Good afternoon. My name is Sandeep Methani and I work in the Urban and Regional Studies Department at IRS. And previously also we met when we talked something about urban sprawl and urban growth modeling. Today I will sharing with you some of the work we have done on urban seismic risk assessment. Urban seismic risk assessment. Uh, If you see, as we discussed, the population of India is, the urban population of India is growing at a very rapid pace. Although, as per the census of India, it constitutes only 30% of the total Indian population. But if you see in terms of number, it is a very huge population. And it is predicted that by 2021, the share of urban population will increase up to 40%. Now, our urban areas are not well equipped to assimilate this rapidly increasing urban population in terms of numbers. And in terms of infrastructure, the things are at just at the seams. They are tearing at the seams. So, what has been the consequence of this growth is that areas which were previously not suitable for urban habitation, due to the population pressure and the rising cost of living, the cost of land prices, slowly people have also started living in areas which are not suitable for urban habitation. They may be steep slopes, dry riverbeds, areas near to industries. They are also hazardous in terms of fire and leakages. So slowly the people are making their homes irrespective. They are not looking at the vulnerability part of these areas, due to which our urban areas are slowly becoming highly vulnerable to hazards. If you see, last time when there was a tsunami, we had a lot of damage because slowly people are also trying to live, making houses in areas which are lying within the danger zones. In hilly areas, due to population pressure in some hill cities, if you see Shimla and some other cities also, houses are coming upon steep slopes also, right? And people are also living, again I told you, on dry river beds also. Due to these things, our urban areas, they have become very vulnerable to natural hazards. And hence, urban areas, they have a high concentration of population. So, in case of a calamity or a hazard, the number is quite high. It is not that if an earthquake comes, it will cause destruction only in the urban areas, it will not cause destruction in the rural areas. There will be destruction. But in urban areas, we have a high concentration of people living in a small area. As a result, the casualty rate will be very high. And secondly, urban areas also, they serve as a service center for the near areas in terms of economic service centers, in terms of education, higher medical facilities also. So we have a lot of population in surrounding areas, which is the entire system is driven by the cities. So if the cities stop functioning, you see, it is not only the cities but also the economy of a large area that will be affected. You see, so there are a number of socio-economic consequences of also. So it is very necessary for us to assess what is the vulnerability of our urban areas to various hazards. Today I will be talking you how we can do a risk assessment of urban areas against seismic activity. That means against earthquakes, how can we do a vulnerability study? We cannot prevent earthquake from occurring. See, earthquake will occur, a tsunami will occur, a volcano eruption will occur. But what can we do? A cyclone may occur also. But what we can do is, we can increase the preparedness of the society, or we can increase our level of preparedness so the losses are minimized. See, so the whole thing is how better we are prepared to absorb the impact of a particular hazard, basically, right? So That is main thing. So all this basically the aim is to increase our preparedness. See, earlier if you see there used to be cyclones in Bay of Bengal. There. So in the coastal areas, we used to have a lot of casualty in terms of human life and destruction to the property. But slowly you see if over a period of time we have made cyclone shelters for people. So now if a cyclone comes, of course we may have this destruction of property, but the human casualty rate has slowly gone down. Why? Because we have increased our capacity to absorb a particular the negative effects of a particular hazard. Similarly, against earthquakes, we cannot prevent an earthquake from occurring. What we can do is, as we are showing in the slide also, we can increase our capacity to absorb a particular phenomena so that it results in less destruction. Ultimate aim is how we can make our cities more safer before a disaster strikes. But there are two terms, one is called a hazard, one is called a disaster. See, the difference basically is any phenomena which is capable of causing destruction to human life and property is called a hazard. A hazard may be natural, it may be man-made also. But when a hazard actually occurs, we say a disaster has occurred, you see. So any phenomena which is capable of harming human life and property is called as a hazard, you see. But when a hazard occurs, we say a disaster has come. Right? So there is a small difference between disaster and hazard when we say. You should be clear basically when we are talking about these terms. When to use a hazard or when to use a disaster term. Right? So you see, this is a whole cycle of you see, after disaster we have rehabilitation, reconstruction, mitigation, preparedness, disaster event relief. See, what we are doing in risk assessment is we are trying to quantify the loss in terms of destruction to the buildings, loss of human life, loss of economy, or maybe some other social impact may be there. So we are trying to quantify the loss due to disasters of various magnitude. So if a disaster of this different magnitude occurs, if an earthquake or different intensity occurs, then what will be the destruction to the city in terms of various terms, law, human life, property. So in risk assessment, we try to quantify them. And why we are trying to quantify them? The answer is we want to be better prepared. We want to increase our preparedness so that we can better absorb the impact of a particular disaster. So this whole thing of risk assessment basically helps us in better preparedness. It helps us in better preparedness, you see. So that's why we are trying to do a risk assessment. So when we do a urban risk assessment, what we try to do is we try to quantify what loss will occur if an earthquake of a particular intensity strikes a city. How many buildings will be destroyed, or maybe not destroyed, they may have damage also, serious damage, minor damage. How many people will casualty will be there, or how many people may be injured. Secondly, which roads will be blocked, which roads will not be blocked, right? So these kind of scenario generation, if you can say broadly, we try to do in risk assessment. And the whole purpose of doing this risk assessment is so that we are better prepared when an earthquake actually occurs. Our risk plans, our evacuation plans, they are better prepared. So this thing only provides a more rational basis for the urban planners on which they can base their planning decisions. The first thing is when a disaster occurs. Now when I'm talking about disaster, let's say we are talking much about the seismic part. See, whenever disaster occurs, it may be seismic, it may be flooding, it may be tsunami, or it may be anything. What are the elements at risk? First we have to find out. You see, if earthquake occurs in an area which is not inhabited, then the elements at risk may be only the flora and the fauna of that area. But the first thing you have to find out is whenever a disaster occurs, see, whenever you try to do a risk analysis, urban risk assessment, first thing you have to find out what are the elements at risk if a disaster of a particular strength occurs. The element at risk mainly are the lifelines of a city. That means the infrastructure. It may consist of the road network, the water supply, the telephone lines, the sewer, the drainage, right? So these are basically called as the lifelines of a city because these are the only lifelines which sustain a city, right? The second things may be the buildings because in a city or in any human habitation, maybe rural or urban, people reside in buildings. We have everywhere there's a building. So the second thing which is at risk is building. The third thing is the population, the people who are living in urban habitation or urban area. And the last thing is the environment of the area. So if you see so before you do a risk assessment, you have to find out what are the elements at risk if a disaster occurs. So they are basically the lifelines of a city, then infrastructure. It will be social infrastructure, physical infrastructure. Physical means the sewer supply, the water supply, the electric supply, the telephone lines, everything is there. Social infrastructure means your schools, your hospitals, post offices, right? Maybe very health center. So these are called as the social infrastructure, that is called the physical infrastructure, and both of them are called as the lifelines of a city because these are the things which are necessary for a city to work. So the elements at risk are the lifelines of a city, the buildings, the human population, and the environment of a city. You can also say the economy of the city, you can say. Of course, we have not included here, but the economy of a region is also at risk if a disaster occurs. Because if a city stops functioning, it also affects the economy of the area also, right? Now you see, whenever we want to do a urban risk assessment, so first you see, it is more of a spatial problem. You see, we want to do urban risk assessment, so we want to find out which areas will be affected more, which areas will be affected less. So the first thing we want to have is it's a spatial problem. We want to find out where are the areas which are located, where are the areas located which are more vulnerable. So the first thing we need before we do a risk assessment is we need maps, and those maps should be updated and of proper scale. If you see in the slide, this used to be a normal river course. The river has flooding has occurred and the water has entered into the city where you can see this yellow line. See, now what you can do is, and this used to be the old drainage channel which used to meet into the river line, right? Now if you have got this set of imagery, you know the extent of the disaster, the extent of the flooding, in fact, you know up to what extent the water has entered the city, of course. What are the features which have been submerged, which have been flooded? You see, if you see it is only the vegetation is flooded, okay. It is possible that some human settlements are also flooded. See? Then what is the kind of activity going on in these buildings which are flooded? If it's a hospital, it's a hostel, yeah, that means it is a serious thing. We have to do something. We have to do evacuation immediately. It may be houses, then also we have to do. Right? If it's a storage or godowns, then we may have loss of this material, but human life still may not be that much lost because it is not used for habitation or any purpose. Right? So you see, if you have got maps which are updated, then it helps you in knowing what is the extent of the particular phenomena and what are the areas which have been affected by it. Like you know, this is the extent of flooding and this is the type of buildings, the activities of buildings which have been submerged. So first thing before we begin any disaster study or any risk assessment study is we must have accurate spatial data of that area, or in turn we must have updated accurate maps of a particular area, right? But you see, our conventional method of record keeping is like this. See, it's mostly in a non-spatial format. It is not that you cannot extract data from it. You can extract, but you see, in case of a disaster, we need data very fast. We need accurate data which is fast. We have to update that data. So extracting data from this kind of storage system, updating is, finding it is very time taking. So the first thing is we should have accurate data of a particular area, accurate and updated data of a particular area. So remote sensing serves as a spatial data provider. It can provide you accurate, updated data of a particular area at various temporal scales, spatial scales, and also at different spectral resolutions also, and different wavelengths also it can provide, which helps you in identifying some features. So remote sensing helps you in, it's more of a spatial data provider. You see that maps can be provided very fastly by remote sensing. Maps can be generated very fastly using remote sensing data. While GIS is more of a spatial data handler. You see, remote sensing provides you data and GIS helps you in handling of that data, storing of that data, querying the data and displaying the outputs, and also those files allocated to other needed people also. You see, so remote sensing and GIS, you see, the remote sensing basically provides you spatial data and GIS helps you in handling of that data. So broadly, this is the role that remote sensing and GIS playing in a disaster management exercise. So to example, you see, remote sensing will provide you this type of data, where using remote GIS, you can generate maps and later you can add different attributes to these maps, right? So keeping these points of view, we tried to do a case study for part of Dehradun, where we try to do urban seismic risk assessment, you see, where we try to quantify what losses if a earthquake of different intensities strike our city. You see, this is basically a map, and this is the municipal corporation map of Dehradun. So for demonstration purpose, we have taken a small area, and this is basically a merged Iconos image we have used. 1 meter panchromatic, a 4 meter multispectral, and finally we have fused them. So we have used remote sensing data of Iconos remote sensing data for conducting our study. Excuse me. Now, same thing is, what is the methodology we have followed? The first thing we have done is, we have assumed a hypothetical epicenter of the earthquake. Then, using different attenuation equations, because when an earthquake occurs, as you go away, you see, from the epicenter, that is the point directly on the earth's surface, below the origin of the, above the earth's surface. It's the point directly on the earth's surface above the origin of the earthquake. And as you go away from the epicenter, the intensity of the earthquake will slowly decrease. The shaking due to the earthquake or the peak ground acceleration slowly decreases as you go away from the epicenter of the earthquake. There are different attenuation equations available. We have used one of them, but you can use any of the equations as per your study area. You can use it. So first thing we have done is, we have assumed a hypothetical earthquake occurs here. This is the epicenter, that means point on the earth surface just above the origin of the earthquake. If this is the epicenter, then we are using attenuation equations. We have calculated how the peak ground acceleration will decrease as the distance from the epicenter of the earthquake increases. Then Using remote sensing and GIS, we have generated different kind of baseline data, we call it. That is map showing the water supply, sewer, road. Of course, road can be easily detected for remote sensing imageries. Water supply and sewer, which are underground, that you cannot see from a remote sensing imagery. For that we have taken help from the local concerned departments. Then we have made try to map the buildings along with their attributes like the age, condition, etc., and try to also collect some information about the occupancy of different houses. So this data here we have used remote sensing a lot, right? For generation of these maps in a GIS environment, we have used remote sensing as one of the major inputs and combined with some ground survey and some data from the sun department, right? So we generated an earthquake, scenario earthquake, and then we using attenuation equation we calculate as we go away from the epicenter how the peak ground acceleration will decrease, or in simple terms how the effect of the earthquake will attenuate as we go away from the epicenter. You see, if there is hard soil it will be faster, but if there is loose soil, there may be sandy soil, the shaking will decrease slowly. Yeah? It also depends on the local soil conditions, how the shaking decreases with distance from the epicenter. Then using in a GIS environment, we have tried to assess what will be the damage to different buildings and what will be the damage to life or damage to various infrastructure or the lifelines of a city. So that's how we go about doing this thing in a 3-part. It's basically the problem is divided into 3 parts. First, to generate a hypothetical earthquake, calculate the peak ground acceleration and its attenuation as we go away from the epicenter of the earthquake. Using remote sensing and GIS, you develop some baseline. Then in a GIS environment, using this hypothetical earthquake and the generated data, you try to estimate what will be the damage to different kind of buildings, what will the damage to different kind of infrastructure, the lifelines of a city, and also you can try to estimate probably how much will be the casualties or other things to human life also. Right? So our study area was a part of Dehradun, that is called as the Dalanwala. What is there? You see, this is the Iconos imagery, and what you see in blue is the houses. Basically, these are the houses, and what you see in red is the red is not vegetation. In fact, it is a major road. By mistake, we have given it a red color, but it is basically the major arterial road that passes through the area. This is the built-up. What you see in cyan color. What you see in this red color is the vegetation, or maybe they may be orchard. Normally they are orchard or trees. And what you see in green, they are vacant. They are vacant plots. You see, vacant parcels of land situated in the area. So using this high resolution satellite data, fused high resolution satellite data, which we got from Iconos, this Iconos imagery, we have tried to generate a land use map of the area. Land use of the area shows, it shows you the outline of the parcels, right? And plus what kind of activity is going on, human activity is going on in each building. It may be a residential, it may be a school, it may be a shop, it may be some kind of a medical activity going on, it may be a religious place also, so it may be a school also, right? Or it may be the area, the land may be just lying vacant with infrastructure. It may be a vacant piece of land with no building built on it, right? So here we have tried to you see, first using this high resolution Iconos imagery, we generated a map or a base map. See, a footprint map is called footprint map means we have digitized the outlines of the building and the parcel boundary. That shows you the footprint, yeah, or some people also call it as a base map. So using Iconos imagery, we first generated a base map. Then using then from ground survey, we tried to find out what is the kind of activity, human activity that is going on in each building, right? So first we generated a land cover map, and then using ground survey, we generated a land use map of the area. You see, a land use map basically tells us what is the activity going on. While using remote sensing, we generated a footprint map. Please clear. A footprint map means it shows you the outline of the various structure, outlines of the various plots, right? So you as a footprint map or a base map onto which later you transfer information and generate a land use map of that particular area. But this all activity was done in a GIS environment, right? So you can see, we also try to, you can also calculate the area also. So these are, in this area you see most of the area is residential area, right? So the residential area is there, followed by, we have a commercial area also, a lot of open spaces also there. Some areas occupied by the roads, you see, what you see in blacks, these are the paved roads. Normally all roads in this area are paved roads. We don't have any unpaved roads. Utility building means they may be used for medical or they may be used for school, and this is the total area of the study area. Right? Second, when we went for ground survey, we digitized the boundary of each building along with the plot, and we also collected some secondary information from the ground, like what is a building type. Building type is, there are two types of buildings in the study area. One is called as a framed structure, other is called as a load bearing structure. In a framed structure we have pillars or we have columns which take the load, and the rest of the walls they are used for partition wall. While in load bearing we don't have columns or pillars, it is the walls which basically take the whole load. So for a earthquake prone area, it is advisable to follow a framed structure, because in case of a seismic activity or an earthquake, the entire structure you see vibrates as a one in a monolithic manner, and we have less chances of a collapse. So you see, in a study area, most of the buildings are load bearing buildings because some of the buildings are very old, while buildings which have come up at a later date, most of them are framed structures. Means we have low of the structure and the walls are basically used for partition, they don't any load. Right? So what we generated these maps, you see, we attached these values as an attribute to each parcel in the GIS environment. Right? The second map shows you what was the roof material, whether roof were made of RCC, that is reinforced cement concrete, or RBC. In olden time, in this area, the old buildings, many of them called as reinforced brick concrete also. So they used to be old, but now most of the new houses, they are RCC, they are reinforced cement concrete. So these attributes we are collecting when we go to the field. This map shows you the age of the buildings also. You see, in this area, a large number are moderately old houses and very old houses only. They also have a substantial number. So this shows you in a pictorial manner, in a graphical manner, what is the location of buildings which are old or new. You see, this data you can also collect in a tabular manner. But when we show the same data in a map format, you see, it helps you in better understanding the phenomena. Whether houses which are old, they tend to be clustered together, or houses which are new, they tend to be clustered, or they are dispersed, intermingled with each other. As we discussed earlier, this data is available in a map format, this raster, this tabular format also. In a register, you can keep in a table format also. But you cannot analyze the data. But if you see the same data in a map format, you can analyze it. Why buildings of a particular type tend to cluster together? Or are they located in a particular region? Is there a phenomena why things have taken place in a particular phenomena? That is the advantage of GIS. It helps you in better understanding of a particular phenomena, because you see things in a spatial format. You can correlate things in a better manner. One more thing we have noticed is the proximity between the buildings. See what happens. Normally some buildings, they have got a dead, so they are just adjacent to each other with no gap. In case of a seismic activity, when the buildings shake, they tend to collide with each other. And that is also a reason for number of damage to the building. So we collected data like how many buildings are situated within 2 feet, 3 feet, 4 feet. We tried to classify them into different categories. And what we found out, like most of the building, they have a distance of less than, you can see from there, 1.5 meter. So if they are too close, sometimes tall buildings, they tend to, they collide with each other. When they shake, they tend to collide with each other. So proximity between buildings is also an important factor. The next thing is, and you see that most of the buildings, they tend to have a ground floor only. So most of the buildings in a study area are ground floor, while those which are located on the a road on the outer skirts, they tend to be ground plus first floor. You see, while buildings which are inside, they are mainly used for residential purpose, and they tend to be more of single story building. A ground floor is also only there. Now, see, using a remote sensing imagery, we have generated a footprint map. Then we have collected data from the ground about the activity going on, made a land use map, collected other data also, attribute data, that may be like the number of stories, the age of the building, the proximity between the buildings, it's a load bearing, and it's a RCC structure. You see, number of activities we discussed. Now we have got a thing called as damage probability matrix. See, in short, we call it DPM. You can see it is written also in the slides. It is called as DPM. What DPM tells us is, if a building has got an attribute like, suppose it is load bearing building, the roof is RBC, the building is asymmetric. Asymmetric means it's not a rectangular square, it tends to have a shape which is not symmetric. Maintenance doesn't matter, and it is old building, then we classify it as a C1 building. You see, on the basis of the attributes which we have collected in the ground, we have classified the buildings into different types: A, A1, B, B1, C, C2, C3, D1, D2, D3. Number of classes we have classified. Then we say, if the intensity of the earthquake is 8, then building A1 has got 0.6% or 60% chance of damage. 60% means the building will have a major structure failure. Now you see that the difference between MMI and intensity. You see, when an earthquake occurs, it's basically a release of energy, right? So that is called as intense magnitude earthquake. You see, magnitude of the earthquake means how much energy is released, and that is measured on a Richter scale using a seismograph. So a seismograph records what is the magnitude of the earthquake on a Richter scale, but how much destruction that earthquake causes, that is as intensity of the earthquake, and that is measured on a MMI scale, that is called, the full form is modified Mercalli intensity scale. So it's quite possible that an earthquake of 6 magnitude on the Richter scale occurs, but one area is having properly built houses, so the destruction will be less. Other house is not having properly built houses with respect to seismic activity, destruction will be more. So they can say the magnitude of the earthquake is same, but the intensity of the earthquake will vary in both areas. Areas which are well built or following standard engineering codes for earthquake activities, they will have less intensity of earthquake. Areas which are not following the code provisions properly, they will have intensity of the earthquake different. Please remember, magnitude tells you the strength of the, how much energy is released on a Richter scale. That's the magnitude of the earthquake and measured using a seismograph. While intensity is a measure of how much damage a particular earthquake causes in a particular area, and intensity is measured on a in India there are number of scales, but in India normally we are following a MMI scale, that is modified Mercalli intensity scale, right, from 1 to 12, right. So we say, suppose the earthquake that occurs, hypothetical earthquake which we have generated, it creates a earthquake of intensity 8. So the building is A1, it will have 60%, that means major structural failure. While building C1 will have minor damage, right? And if the earthquake intensity is 10, suppose, then building A means building A will have a total collapse, building B1 will have a total collapse, and only building D2 it will be means it will be major damage failure. Then you can find out what are the attributes of this. So this is called as a damage probability matrix. In short form, people call this DPM. So we collect data, generate a database in a basically in a GIS, and then we say if this is the attributes of a building, we classify them into different types using based on the DPM matrix, and then we generate various hypothetical scenarios. If an earthquake of this much intensity occurs, what will be the damage to various building types? That is normally how we attempted to do a urban seismic risk assessment. What is the damage to different kind of buildings in our structure area in case of earthquakes of different magnitude? So you see, if an earthquake of 6 strikes, then there will be little or no damage in our study area. But if earthquake of intensity 7 strikes the city, our study area, then some buildings will have little damage, but quite a few buildings will have minor damage. Right? If an earthquake of 8 occurs, then you see the area with minor damage, building minor damage have slowly gone up. Right? And in case of earthquake of intensity 9, you see the damage starts decreasing. The damage rate will start increasing. You see. In case of 10, you see some buildings will start collapsing also. Some buildings will collapse also, and the damage rate to other buildings will start. And at the intensity of 11, the buildings which are collapsing, they will increase dramatically. Now what we have to correlate is, if a building collapses, what kind of land use or what kind of activity, this data already we have collected, showed you earlier. Now we have to correlate is, suppose a building collapses, as you are seeing it here. If a building collapses, then what kind of activity is going on in that building? If it is a building which is housing a school or a hospital or any other crowded place, then you see our casualty rates will be high. So in terms of preparedness, what we have to do is either we shift the school, shift the hospital, or we try to do some kind of retrofitting. Retrofitting is we try to increase the strength of the building so it will not collapse. So first you do a urban risk assessment, and then you correlate it with the kind of activity that is going on in that building. As a result, you can find out buildings which are collapsing, what kind of activity is taking place at earthquakes of different intensity. And this inputs basically will go as an input when you make a disaster plan, a disaster evacuation plan of a city. Then you are better prepared. You know what will happen if an earthquake of 11 occurs, which building will collapse, and what is the kind of activity that is going on in that building. So you know better what now. This is what I showed you previously in a map format. This is in a tabular format. You see, earlier also I was saying, this gives you figure, but if this same thing is expressed in a map, it helps you to better understand the phenomena. You can know how buildings which are near to which are collapsing, are they near to each other? Are they clustered in a particular area, or they are just spread randomly in my study? You see, that is the advantage of using a GIS or doing things in a spatial format. And this map also shows you the ownership and tenancy of this. Sometimes post earthquake we have to give relief also, so we know who is the owner of the land, that particular building, who is the tenant. It helps in those cases, especially if you want to do compensation and all those things. Secondly, we can also generate different queries, like if this is a residential building, you see, one thing is you do assessment, but sometimes you can query a GIS database also. You can say I want to find the buildings which are residential, close proximity of each other, which are asymmetrical in shape, which have got a very poor maintenance, which are moderately old, load-bearing earthwork. Please show me the location of those buildings, and we will find out there are 463 houses, and they tend to be clustered. You see, they are clustered in this area, and they are clustered in this area. Now you know that when you're seeing things in a map format, you know buildings which are very vulnerable, they in fact are, they tend to cluster together. You see, they are clustering together. Why? That reason then you can find out why they are clustering, right? Or if you do retrofitting, you know exactly that I have to work in this area only, where most of the houses which are satisfying this criteria are located. Then you can again generate a query like buildings which are residential, which are situated at more than 4 feet from each other, symmetrical in shape, maintenance, newly built, framed structure. Where are those? You will find this. These buildings are not clustered. In fact, these buildings are spread out in the area. You see, while buildings which were satisfying our earlier criteria, they tend to cluster in a particular part of the study area, right? So you know, like if a earth occurs, then I more loss of property in this area, and in this areas there will be relatively less. So you see, you know the phenomena, how it is spread in a particular area, how the losses will be spread. This thing you can do by using a GIS. Yeah. Secondly, what happens when an earthquake occurs? The road gets blocked. So earlier we tried to quantify how the buildings which are having different kind of losses, they are situated in the study area. Now we are trying to estimate which road has a high chance of blockage if an earthquake occurs. So first, using remote small data, we have found out the road type, the road width, 3 meter, 5 meter or maybe more, and the roof material, it is asphalt or non-asphalt. Then what we do is, see, a 3 meter road, we have generated a buffer on both sides of the road. Similarly, for 5 meter road, we have generated a buffer on both sides of the road. And for a 9 meter road also, we have also generated a 6 meter, we also generated a buffer. Now what we do is, we have generated a buffer around the road, and in this, if in this buffer, buildings tend to have a high collapse rate, and the road width is very small, there is a high chance that this road may get blocked because of the debris. And if the road is blocked, you cannot carry out any evacuation, rescue and relief operation, right? So, if in this buffer narrow road, buildings they tend to have very minor damage, then we know that there is a high probability that this road will not be blocked, and still we can carry out rescue and relief operation in this particular area. See, so what we have done is, we have created buffers on both sides of the roads, and in this buffer buildings which are situated, we have estimated what type of losses they have. If all buildings on the both buffer, they have got, the road is 3 meter only, and all the buildings they are collapsing, that means this road has a high probability chance of blockage. But if it is a wide road, we are 9 meter roads, and some buildings are collapsing in the buffer, that means still there is a chance that this will not be blocked, and still we can carry out rescue and relief operations by using the road only. So you see, we created a buffer, and then we estimated what are the buildings which are situated in the buffer, what is the damage rate, and on that basis we try to generate a map which shows which area has a high, which roads basically they have a high chance of probability of blockage, which roads they don't have a high chance of blockage in case of a seismic activity. Or then earthquake, you can also say at earthquake of intensity 10, which road will be blocked, earthquake of intensity 7, which will be blocked. Again you can say, generate scenarios and earthquakes of different intensity will result in blockage of which road, and which roads will not be blocked at this particular intensity of the earthquake. See, earlier we had made for 10, now we have made for, you can again generate scenarios, and as I discussed earlier, this all provides a rational basis on which you can take decisions regarding your city planning or the evacuation which you develop for your city. What I showed you in the map format, same thing we have created in a tabular format. Right. This is just an idea where we have draped on top of the satellite imagery. You see, if this is the roads, what you see in brown is that this road has a high probability of blockage, that this road will be blocked, but these roads will still be open. These buildings will collapse and this will be the area which will be affected by them. Now what we are trying to show you is which road has a very high chance of blockage at a particular earthquake, intensity of particular earthquake. If you have got a hospital situated here, then in the time of earthquake, that hospital will not be functional because you cannot reach that hospital by road. Neither you can bring people or neither you can take out the people who are wounded or wounded basically, right? The solution is either you create another road or you try to shift the hospital, right? If you are trying to have some medical ambulances located here, then even then these ambulances won't be able to get out of the area. They can't move because the road is blocked. Again, we try to show the same results in a 3D format. This shows the building height and gives you an idea like this road is going to be blocked. Again, this shows the same area. See, this road, because it's a narrow road and it has got tall buildings, high buildings on top. In fact, this is a major commercial area of Dehradun. So in case of a seismic activity, this road has got a high chance of blockage. And since it is a commercial area also, so a lot of people may get trapped here also. But this road will be there, but still this road will be open and we can use this for rescue and relief operation. This shows you the day and night population of study area. See, if it is a commercial area and the earthquake strikes in the night, there will be less loss of human because people will go back to their residence. But if it is a residential area and the earthquake strikes in the night, we will have more casualty because people have come back to their home from work. So sometimes the time at which the earthquake strikes also determines your casualty rate also. So this is just in a graphical format. We have tried to show the distribution of the day and night time population in our study area, right? So this is all where we have tried to, where we attempted to do some study regarding the application of GIS and remote sensing in the field for urban risk assessment, and these maps can be used for various planning exercises also.